and thank you for joining us today for the next edition in our Blue Carbon in Practice webinar series, bringing coastal wetlands into the U.S. National Inventory of Greenhouse Gas Emissions. I'm Stephanie Simpson with Restore America's Estuaries. On behalf of our presenters, our staff here at RAE, and our co-sponsor for this webinar, the Coastal Carbon Research Coordination Network, I'd like to thank all of you for joining us. Before we begin the presentation, I have a few quick announcements. First, all participants will be in listen-only mode. If you are having any issues or technical problems, you can press *0 for operator assistance. We will be recording this session, and the webinar recording will be posted on our webpage, which will be shared with all webinar registrants. Following the presentations, we will have a moderated Q&A session. At any point during the webinar, you can enter a question into the chat or question box in the webinar screen, and we'll work to answer as many as possible following the presentation. If we don't get to your question, you can email me at ssimpson@estuaries.org. My contact info and our presenters' contact info will be listed at the end of the webinar. And finally, we have a brief 3-question survey at the end of the webinar. You will be prompted to answer these upon exiting the webinar, giving you an opportunity to provide us feedback on today's webinar and make suggestions for future webinar topics and speakers. And we appreciate this feedback so we can continue to provide you with relevant blue carbon information. For those who are new to Restore America's Estuaries, a quick background on us. We are a national nonprofit dedicated to the protection and restoration of our nation's bays and estuaries as essential natural resources, and we lead an alliance of 10 conservation organizations across the U.S. One program area we work to achieve our mission is our Blue Carbon National Initiative. And for a very quick review, blue carbon refers to the greenhouse gases stored in, sequestered by, and released by coastal marine ecosystems, including seagrass meadows, mangroves, salt marsh, and other tidal wetlands. Today's webinar will not be going into the basics of blue carbon, so if this is a new topic for you, I encourage you to check out our archived webinars on blue carbon, which can be found on our webpage at www.estuaries.org/bluecarbon. While there, you can also sign up for our monthly Blue Carbon Buzz e-newsletter to keep up to date on blue carbon events, webinars, publications, and more. With that, let's get started with today's webinar topic. As I mentioned before, I'm Stephanie Simpson. I manage the Blue Carbon program at Restore America's Estuaries, and I will be acting as moderator for today's webinar. And I'm happy to introduce our presenters for today. Dr. Steve Crooks is Principal for Wetland Science and Coastal Management at Sylvestrum Climate Associates. He's a wetland scientist with over 20 years of experience in the science and practice of wetland restoration. Steve was a lead author of the IPCC 2013 Wetland Supplement, is a NASA Carbon Monitoring System Principal Investigator, and co-founder of the International Blue Carbon Initiative. Steve is also the lead PI for the effort to include coastal wetlands into the National Inventory, and we're fortunate to have him today to speak about this effort. We'll also be joined today by Dr. Meredith Muth, the International Program Manager for NOAA's Climate Program Office and a key partner in this effort to incorporate coastal wetlands into the National Inventory. So with that, I'd like to go ahead and turn it over to our speakers. So I'll be giving presenter controls to our speakers now. And I'd like to hand it over first to Meredith for a few words of background on this effort. And Meredith, just a reminder to unmute yourself when you're ready.
Stephanie, can you hear me now?
Yes, that's great. And I'll pass it to you, Meredith.
Can you still hear me?
Yes, we can hear you well.
Great, thank you. When NOAA started working with EPA and Restore America's Estuaries, we had this very ambitious goal of including coastal wetlands in the U.S. Greenhouse Gas Inventory for the first time. And NOAA saw this topic as highly relevant to multiple programs that we have on coastal habitat restoration management, as well as climate mitigation and adaptation. But we recognized immediately that we needed multiple skills and expertise to cover this, again, very ambitious task. Next slide, please. And one of the first things that we did was establish a coastal wetlands carbon working group. And do I have control of the slides? Thank you. And you can see, looking at the list of names right there, is a very diverse group of both federal and non-federal partners. And we were also incredibly fortunate enough to have recruited Dr. Steve Crooks to lead this incredible motley crew. And so I don't want to take up any more time. Steve, I'm going to pass this on to you, and thank you all for joining us today.
Thank you very much, Meredith, and thank you, Stephanie, and thank you everybody for joining. So I'm going to give you a little bit more detail on the work that this entire group has pulled together. And as we've been thinking about how to include coastal wetlands and how we manage coastal wetlands and incorporate that into the national inventory of GHG emissions and sinks. So by way of some background, over the last 20, 30 years, there's been interest in including the biosphere within and how we manage the biosphere within national accounts. It's really began with forestry and is heavily focused on forestry. But then around about 10 to 15 years ago, soil scientists and wetland scientists said, well, you know, really we should also be including soils much more fully in our accounting and as we manage the biosphere. And then around about 5 to 7 years ago, coastal wetland scientists said, well, you know, coastal ecosystems also have significant stores of carbon in biomass, but even more so within the soils. We should think about including recognition of how we manage these ecosystems too. And so I'm going to tell you a little bit of that story and how it became part of the US inventory. And this figure here, just to illustrate, you know, what we're talking about when we think about coastal ecosystems. This salt marsh right here happens to be almost outside my house here in San Francisco Bay. And each year, tidal wetlands accumulate carbon in the form of CO2 from the atmosphere through plant material. Oops, sorry about that. And part of that becomes buried within soils. And so this soil face here, creek bank, represents maybe 1,000 years worth of organic and mineral accumulation and carbon stores which are built up over that time. The amount of carbon accumulation each year is relatively small, of the order of between 3 to 6 tons of CO2 per hectare per year, but it accumulates over time. And when you drain or convert a wetland to something else, that's when significant emissions can happen. And you may release several thousand years worth of carbon just within a few decades. The same principles apply equally for mangrove systems and to some degree also for seagrasses. A few years ago, this study was published in 2012. A number of scientists came together to estimate what are the global emissions associated with the loss of coastal wetlands around the world. Many countries actually destroyed their coastal wetlands many decades ago, but particularly in the tropics right now, conversion of wetlands is progressing at quite a pace. The cutting to the chase of this story, if we look at tidal marshes, mangroves, and seagrasses and estimate a rate of loss and the legacy effect of drained organic soils, it's estimated that approximately 450 million tons of CO2 are released each year from these drained and converted wetlands. Now, how big is that? That's roughly the size of the emissions from the economy of California or Poland or the UK. But our error bars are very large. You know, it could be as low as 150 million tons, could be as high as 1 billion tons. So there are questions here, and so with countries now including or potentially including coastal wetlands within their inventory, it'll allow us to understand the scale of these emissions now, where they are occurring globally, and help us then develop better management strategies if required to reduce those emissions moving forward. By good fortune, the IPCC in 2011, as this story was emerging, was also looking to update their guidance on greenhouse gas accounting, including wetlands. Up until previously, wetlands were only partially recognized within the guidance provided to countries developing their inventories. And in 2011, it was scoped out that further guidance was ready to provide on wetlands. At that time, there was a request that coastal wetlands also be included within this process. So what does an inventory look like? Well, this is the summary that came from the US inventory in 2017, which covers all the way through from 1990 to 2015. So it lags 2 years behind the year of publication. As we can see, that most of the economy, the emissions occur, of course, from the energy sector. Overall, there are emissions of around about 6.5 billion tons of CO2 each year. That has declined over the last few years and is roughly now about 3% above the 1990 levels. The biosphere, the land use, land cover change aspect of the inventory is actually a net sink to the tune of around about 780 million tons each year. So a very important contribution to the net fluxes for the US. The guidance that the IPCC provide to nations in terms of their greenhouse gas inventories is intended to be used globally by all countries who report back to the UNFCCC. The guidance provides default data and methods, which allows countries to focus resources to target the largest sinks and sources within their boundaries. It provides standardized methods so that QC, QA analysis can be provided, and it allows transparency and accuracy in comparison across countries so that we know that we're comparing apples to apples when we look at the data. The guidance also allows countries to use more sophisticated methods should parties choose, if they can go beyond and provide more highly refined analysis to support the inventory. Well, how are inventories developed? Well, the basic component of an inventory, particularly related to land use change, is the quantification of activity data, and you multiply that by an emissions factor. So for land use, activity data commonly comes in the form of some measure of land use change, conversion of forest to cropland, conversion of wetland to settlement, some measure like that. And then that is multiplied by an emissions factor associated with either a stock change in carbon for the various carbon pools, biomass, deadwood, litter, and soils. And that together is then aggregated to form an emissions estimate, which is then scaled up to the national level. It sounds very simple, but in actuality, there's a lot of work that goes into developing these accounts. And we'll cover some of the detail of this. The IPCC guidance allows countries to apply 3 different tiers of analysis. At the simplest level, a country might apply a tier 1 level assessment. And under such conditions, they may utilize default values provided by the IPCC from global data sets, which allows them to apply emission factors, as well as standardized approaches for estimating activity data. At a tier 2 level, a country may use locally specific or country-specific data that is relevant to them in terms of their analysis. And at a tier 3 level, a country may apply higher level resolution analysis, including more detailed spatial analysis, as well as detailed modeling to estimate fluxes and changes in carbon stock. For the analysis that we have done under the US inventory this year, we have focused our analysis at this stage only on the soil component, which is the largest component for coastal ecosystems. Much of our analysis is at the tier 2 level in terms of activity data, which is highly resolved spatially. We have nationally specific carbon stock and flux data, but we have applied some tier 1 assumptions related to depth of impact. And I'll come back to this in the areas where we can improve the inventory moving forward. So for the land classifications that are included under agriculture, forestry, and land use, which is chapter 6 of the inventory, the sectors which are include forest lands, croplands, grasslands, settlements, wetlands, and other lands. And we should be focusing on the section, of course, related to wetlands, but specifically coastal wetlands, which is the first part of wetlands that we've included in this year. The IPCC 2013 supplement, the wetlands supplement, it provides guidance on terrestrial as well as coastal wetlands. It primarily focuses on cross-cutting guidance for organic soils in terrestrial systems, but also re-wetting. But under chapter 4, there's guidance provided to those wishing to do the inventory related to coastal wetlands. There was also additional guidance on other freshwater wetlands, constructed wetlands, and good practice for reporting. Under Chapter 4, the following information is provided. For nations that would require assistance with estimates of carbon stock for mangroves, there is data provided on living biomass within mangroves as well as dead wood carbon pools. There is generic method and guidance and data provided on CO2 emissions and removals on coastal wetlands on both organic and mineral soils for various management activities, which I'll come to. Also included, which is new, is the N2O emissions associated with aquaculture use. Aquaculture construction is covered under the excavation part of CO2 emissions, but the food stock applied to aquaculture results eventually in a release of NO2, and that is the guidance is provided here. There's also methane emissions guidance provided for rewetting and creation of mangroves and tidal wetland marshes. When we look at specifically the activities which guidance is provided for coastal wetlands, they fall into the following sections. The impacts of forestry management on coastal wetlands, particularly related to biomass. The impact of extraction and drainage on biomass and soils. The impacts of wetlands rewetting and revegetation and creation. And also just revegetation activities under undrained soil conditions. And the non-CO2 activities, as I mentioned, N2O emissions from aquaculture, as well as methane emissions associated with the revegetation, rewetting, and creation of tidal wetlands. And so we'll be looking at several of these as we delve into the US inventory. So which emissions and emissions removals are of interest to us within the US? Well, we're actually interested in emissions and removals of CO2 and methane on intact and restoring wetlands across the lower 48 of the US. And the reason we're interested in all of these coastal wetlands is that the US considers all coastal wetlands to be managed, in part because of their proximity to human populations, but also because of the level of regulation and oversight provided to these coastal ecosystems. We are interested in the impacts of drainage and excavation on carbon stocks. We're also interested in the impacts of conversions of coastal wetlands to open water. While open water in many conditions is recognized as a wetland, there is a loss of carbon stock associated when a vegetated coastal wetland is converted to open water. We are interested in forestry activities on wetland soils. However, we lack data to recognize the impacts of clear cutting of a forest, say, and how that affects a wetland soil. There is some data globally that this is an impact, but we do not have data to include within the inventory at this time. We are also interested in methane emissions from impounded waters. When a barrier is built in a coastal area, fresh water impounds behind it, which leads to a methane emission. This is something we'll see hopefully as a part of future improvements, but is not included within the inventory at this time. Aquaculture, as I've mentioned, is something that is included within the inventory, but is a relatively small emission for the US, and I will come back. The data that we've called upon is derived from the NOAA Coastal Change Analysis Program. It's a regional land cover and land cover change data set. It's been it's developed from Landsat data. It's been updated every 5 years since 1996, and so we have a time series currently extending through to 2010. And in production currently is the development of the 2015 data set, which will be rolled into the inventory in coming years. The data set is reviewed and QC'd in-house by NOAA, and so we have a sense of the accuracy of the product and the degree to which it covers, it recognizes land cover change on the land surface appropriately. It covers 25% of the lower 48, and we use this to provide a subset for coastal wetlands data. And it provides relatively high degree of data classification for subsets of coastal wetlands within the US, a higher level resolution than is provided by other data sets. So how do we do this? The first thing we need to do is define the coastal land area, which is based upon the extent of tides around the US. So effectively, we cut the CCAP data set. We use LIDAR data, and tidal data, to then map where the highest extents of tides are, and map those lands, wetlands, and other lands which fall below that elevation. We quantify the various types of land use within this coastal land area. And I should mention actually that the seaward extent of our coastal land area is the seaward extent of intertidal wetlands. So we do not recognize subtidal ecosystems at this time within the inventory. We quantify land use change from 1990 to 2015. As I mentioned, we have a 2005 through to 2010 data set, which means we have to extrapolate trends beyond that to 1990 and 2015. Our data is focused on the soil component at this time, though biomass will be rolled into the next version of the inventory this year. We ascribe a CO2 and methane emissions factor for land use change as appropriate, and we calculate annual emissions or removals under the classes of wetlands remaining wetlands, wetlands converted to open water, and other lands converted to wetlands. And this is what the data looks like. Here you see the land, the coastal land area for the lower 48 of the US, with examples from San Francisco Bay, New Orleans, and Chesapeake Bay. If we zoom into San Francisco Bay, this is what the CCAP data looks like. The pinks and the purples represent different types of coastal wetlands, with the browns, tans, and yellows representing agricultural land, which is now below sea level. And that agricultural land back in time would once have been coastal wetlands. Now, under the inventory, we only do the accounting for the fluxes on the coastal wetlands. The croplands and grasslands, where appropriate, already account for ongoing emissions from organic soils under their land use category. So what does the land cover look like? So the total land area for the coastal US is just under 89,000 square miles. Roughly 78% of that is open water. If water is ignored, 87% of this land area is actually vegetated wetland. Only 6% is agriculture, and then here you see the other values for the land uses. So one of the interesting findings actually from this analysis is that for the coastal land area, a relatively high proportion still remains as intact wetlands in some form and is not being converted to other land uses. This is a relatively high proportion compared to other parts of the world. Using all data from now on, I'll mention is in hectares rather than square miles. Apologies for swapping backwards and forwards. So here we look at the different land cover classes and area and types of soils that we find in the coastal land area. And there's a certain area of developed land, 151,000 hectares. Then there are drained former wetlands, cultivated lands, grasslands, and also forestry, which is on dry lands below below the tide elevations, behind levees. And then we have two types of wetlands: palustrine forest, scrub shrub, and emergent wetlands, which are non-tidal, dominantly non-tidal freshwater systems, and then estuarine wetlands, forested again, which include mangroves, scrub shrub, which also includes mangroves, and emergent marsh. And they represent the dominant areas of ecosystems within the coastal land area. Now, if we look at the organic soils and estimate the amount of CO2 that's been emitted each year then approximately 5 million tons of CO2 is being released ongoing from these drained organic soils around the US. And as I mentioned, this is accounted for under the other land uses, the other land use categories of the inventory. But it reflects an ongoing emission that continues. In terms of methane emissions through impounded waters, here's an example. This happens to be Herring River in Cape Cod, and with a barrier that blocks off former tidal flows. It's estimated in a paper that's in review currently that between 1 and 3 million tons of CO2 equivalents each year of methane emissions are emitted back to the atmosphere by a lot of these small-scale tidal impoundments around the US. This is not currently included in the inventory until we have more refined analysis. The net fluxes, of course, from coastal wetlands, remaining coastal wetlands, are as follows. Vegetated coastal wetlands, remaining vegetated, so effectively those which are still intact within the environment, represent a net sink of 12.1 million tons of CO2 each year. The conversion of vegetated coastal wetlands to open water, so effectively erosion which takes place, represents a net emission of 3.5 tons of CO2 each year. And I'll come to the ranges in a little while. Open water, so effectively restoration, conversion of open water to vegetated coastal wetlands represents a relatively small carbon flux of 0.015 million metric tons of CO2 each year. And I'll come back to the relevance of that later. Methane emissions in the palustrine wetlands represent 3.6 million metric tons of CO2 each year. And aquaculture represents roughly about 0.1 million metric tons of CO2 emissions each year. Looking at the ranges of some of these values to give a sense, the conversion of wetlands, vegetated wetlands to open water, from 1990 through to the extrapolated values for 2015, but really through to 2010, we see a range of emissions between 1.27 and 7 million metric tons each year. And this reflects actually the impacts of the reduced resilience of the Mississippi Delta, where most of these emissions are taking place, and the periodic impacts of hurricanes, which mobilize en masse wetland soils due to erosion. Wetland drainage has also been quite variable, representing just under 1 million tons to almost 1 million tons of CO2 released each year, which is an interesting value considering that we have a no net loss policy, which affords a certain level of protection to coastal ecosystems. And I'll come back to that. Wetlands restoration, as I mentioned, represents a relatively small restoration of carbon sequestration around the US. And so effectively, we see 100 times more emissions taking place through drainage of wetlands than we are putting back in the ground through our restoration activities. So summarize the data in a similar sort of way, but to draw out other messages. As we think about the remaining carbon stock we have within US coastal wetland soils, within the top 1 meter, which is our default value for analysis, the US holds still 3.2 billion tons of CO2 within these stocks. So that is the magnitude of the pool that could be released if these wetlands were drained or eroded. Coastal wetlands sequester, as I mentioned, 8 million tons of CO2 each year. And drainage emits between 0.7 to 1.9 million metric tons of CO2 each year. And the organic former coastal wetland soils emit 5 million metric tons. Methane emissions from disconnected tidal waters are approximately estimated at this stage to be between 1 and 3 million metric tons, and wetlands erosion releases around about 3.5 with a range of 1 to 7 million metric tons each year. And restoration accounts for a small amount, of 0.01, 0.02 million metric tons of CO2 removed from the atmosphere. However, if we think about restoration activities within the coastal US, it's important to recognize where they occur in the landscape when you think about what their real impacts are. If you restore a coastal wetland on, for instance, an organic soil which is emitting CO2, you'll lead to a stop loss of those emissions. Equally, if you restore a coastal wetland by removing a barrier which allows tidal saline water flow again, then you reduce those methane emissions at the same time. So a number of these things are cumulative together. So when we think about wetlands restoration projects, we should not only focus on the small value at the bottom, but also recognize how those values are actually cumulative or aggregative with other GHG impacts of those restoration activities. But we should also recognize that the importance of conserving and protecting existing wetlands in terms of the carbon stock, just to recognize, of course, that it's the emission side of the equation which is larger than the sequestration part of the equation. So what do we know now that we didn't know when we began this process a couple of years ago? Well, an important lesson really is that it is possible to include at least tidal wetlands within the national GHG inventories. The US has been successful at protecting significant extents of national coastal wetlands through historic legislation. And this has protected coastal stocks, though existing wetlands are threatened by future sea level rise. Even with the no net less policy, drainage continues within a certain area of coastal wetlands around the US, which is leading to an emission that is taking place. And that emission, as I mentioned, is roughly 100 times greater than the sequestration that we see with restoration projects. The implications relevant to resource management actions. There is an opportunity for agencies to include GHG emissions and removals within their resource management actions through improved quantification. So it's an additional ecosystem service that we can recognize, as well as all the other ecosystem services associated with our land management. There are particular opportunities to reduce emissions, primarily through reducing erosion of coastal wetlands, particularly in the Mississippi Delta, where erosion is ongoing, in large part due to historic sediment management activities upstream. There is the opportunity to reduce drainage of coastal wetlands. There's also the opportunity for restoration to happen on drained organic soils, which has the stop loss effect, as well as removing barriers and reconnecting impounded waters to tidal flow to reducing methane emissions. What are future research needs that are falling out of this work? We use tier 1 values or assumptions when we think about the level of the depth to which soils are impacted, either by drainage or by erosion of coastal ecosystems. We use a default value of 1 meter in this regard. This is probably relatively representative for the Mississippi Delta, but as we've seen in several parts of the country, when we think about drainage, for instance, the Sacramento Delta near where I am, drainage of those organic soils has gone down at least 6 meters in that area. So we would be underestimating the impact under such conditions. We do not have information on the impact of forest clearance on wetland soils, and that's a gap that would be useful to improve upon, to fill. Methane emissions from impounded waters, we have good modeling analysis, but we have relatively little data on emissions of methane beyond default values for coastal impounded wetlands. And though representing over 1 million hectares, there's relatively sparse data on carbon stock accumulation rates and methane emissions rates from coastal wetlands, palustrine coastal wetlands around the US. understanding this at this time is that roughly it's a net balance. Carbon sequestration equates methane emissions in a CO2 equivalent context, but that data can be improved upon. And in a broader lesson that has emerged from this work and parallel work is that within the science community, we still consider different parts of the landscape as separate entities to a large degree, maybe providing boundary conditions for different analysis. You know, the terrestrial, the wetland, and the aquatic ecosystems are still considered relatively separate within science programs. And while there is some research, or there is considerable research, but not enough, describing fluxes of carbon across these boundaries, more would be helpful for us understanding the flows of carbon across coastal ecosystems. And so we suggest more work would be helpful in this regard. What are the broader implications, both for the US, but also abroad? As I mentioned earlier, if we account for our methane emissions, we can determine our CO2 and methane emissions in coastal ecosystems and how we manage them. We can improve, if required, the management of coastal ecosystems based upon an understanding of those fluxes. The US has demonstrated that it is possible using freely available data and a relatively complicated coastal system such as the US to get a reasonable estimate of what our carbon stock change and methane emissions are for our coastal ecosystems. And so the same data is available to other countries, and they could apply these same procedures should they choose to recognize the stock changes and methane emissions for their coastal wetlands. We should also recognize that within the US, the policies of protecting coastal wetlands have been important in minimizing emissions. As I mentioned, there's over 3 billion tons of CO2 held within just the top 1 meter of soils within the US. And when we look at some other parts of the world where this protection does not exist, the US has been successful in maintaining a relatively high area of intact coastal wetlands and protecting those soils. For other countries, excavation and drainage will be a much more significant part of their inventory. And so, as I mentioned above, they have the opportunity to recognize those fluxes and recognize the opportunities for management within their national boundaries. But a broader lesson or observation is that the wetland supplement that we applied, developed by the IPCC, does not provide specific guidance on erosion of coastal wetlands. And though we've included it within the US inventory to demonstrate the scale of the emissions, this is something that could be included potentially within future updates to the wetland supplement. And for some countries, this may be a significant source of emission from coastal wetlands. Challenges. Technically, the challenges that we ran into, which we're going to be working on moving forward, is the complexity of integrating wall-to-wall spatial data that is provided by the CCAP data set with other data sets that rely on either plot data dominantly or rely on survey data, which is supported by also spatial data sets. But we have a number of complex data sets that we're trying to merge together across to represent the entire US land representation. There's also challenges as part of the process for the accounting to include the trend changes that when you go from one land use category to another, there's a transition period of 20 years. And for wetlands, this can be complicated in that it might go through several phases, or land use change may occur several times within a 20-year period. It's not a very large impact, but this is something that is providing technical challenges within our experience. We have had to interpolate and extrapolate between only 4 data epochs for land cover change. And one of those data points represents 2 hurricanes that occurred within the Mississippi Delta. And that has shaped the trend information that we have for the coastal ecosystems of the US. This data set will be improved upon when the 5th data epoch comes out for 2015, probably in 2018 or 2019, but that has been a challenge for us. And we remain limited in terms of data, as I mentioned, for the extent of seagrasses. Particularly, we do not know the current extent of seagrass and seagrass change since 1990, which has prevented us from including that within the inventory. We are relatively data sparse for palustrine wetlands. We are data sparse for the impacts of forestry activities on coastal wetlands, methane emissions from impounded waters, and we could have improved understanding of the magnitude and the fate of eroded carbon from coastal ecosystems. Planned and potential improvements down the line. This year, we will be including biomass for tidal wetlands, or these tidal marshes within the inventory. This data set is being provided by a parallel project funded by the NASA Carbon Monitoring System as well as the US Geological Service, which I'll come back to in a moment, which is helping us with refined data sets for carbon stock change for the continental US. And this project is due to be wrapped up this year, 2017. The Blue Carbon Monitoring System project is also helping us with additional data sets on carbon stock change across the country. And we intend to continue to work to improve the harmonization of the CCAP data set along with the NRI and FIA data sets. Potentially down the line, though considerable work would be required to do this, would be inclusion of seagrass meadows within the inventory. That is an aspiration that we hope to achieve down the line, but is not in the near term. Potentially, we hope to include also improved carbon and methane flux analysis for palustrine wetlands, improved quantification of fluxes associated with impounded waters. When data becomes available, we'd like to include more information on the impacts of soils and forestry activities, and inclusion beyond the coastal land area of terrestrial wetlands. Currently, some aspects of peatlands are included in there, but large parts of the US terrestrial wetlands are not included within the inventory at this stage. Just to mention some things coming online in the near future. As I mentioned, there's the Blue Carbon Monitoring System project, USGS and NASA funded, which is in the process of providing a higher resolution data set of carbon stock change for natural wetlands, as well as looking at both the biomass and the soils, and is helping to connect that together with the more refined analysis of land cover change using both the CCAP and other data sets. And we shall be rolling in the results of this project to some degree this year with the biomass, and in coming years with more refined analysis on the soil carbon pools. Also of potential interest is the National Science Foundation has funded a coastal carbon research coordination network. This is a network that will support further communication and data sharing between scientists, primarily in the US at this stage, but also internationally. Data sharing on the carbon stock change, as well as other gas fluxes. But an important component of this, which will be hosted by the Smithsonian Environmental Research Center, is the creation of a national data archive for blue carbon or coastal wetland carbon information. This data archive is in development right now, and hopefully in the future will be extended and be available to international partners also down the line. So we'll stay tuned there. I would like to thank for support for this work. It's been provided by NOAA by various officers of NOAA, National Oceanographic Service, the Oceanic and Atmospheric Research, and the National Marine Fisheries Service, who made this work possible. And I would also like to thank the project team who have worked on this project, who have been invaluable and have made it possible for this work to move forward. I particularly would like to recognize Tiffany Troxler from Florida International University, Tom Worth from the EPA, who has provided a lot of guidance to help us move forward, Nate Herold, who's been responsible for much of the analysis for the NOAA CCAP data, along with Meredith Muth, Ariana Sutton-Greer, as well as input from Amanda McCarty. And from the Smithsonian Environmental Research Center, a lot of very important underpinnings to this analysis was provided by Blanca Bernal, James Holmquist, Meng Lu, and Pat McGonigal. And finally, but not least, I would like to thank Steve Emmett Maddox and Stephanie Simpson at Restore America's Estuaries for managing this project. And I think with that, yes, I hand it back over to Stephanie. Thank you.
All right, thank you very much, Steve and Meredith, for taking time to talk to us today. I'd like to go ahead and open it up for some discussion to answer your questions. If you have a question, you can write your question in the question or the chat box. In addition to Steve and Meredith, we also have on the line another member of our Coastal Wetland Carbon Working Group, Dr. Ariana Sutton-Greer at NOAA, to help with our question and answer session. So I'll go ahead and ask some of the questions that have come up. The first, I believe, is in reference to the slide on coastal land area, land use and soils, asking which length, water, and ground component coverage of the coast is considered as coastal wetlands.
So we recognize at this stage all wetlands that fall beneath the elevation of highest tides. And so this included effectively two different types of wetlands. It included those wetlands which are connected tidally, and those wetlands which fall behind coastal barriers, levees, dikes, but are still maintained in a wetland state. And so we accounted for the emissions and removals associated with management activities on all of those kinds of wetlands. Now, it may be in the future that the wetlands which fall behind dikes get incorporated into another part of the wetland inventory. It may be recognized, for instance, as being part of the sort of terrestrial wetland areas. There would be no double counting at that time if that were the case. It would just fall out of the coastal wetland part. But as we recognized all wetlands as those below the elevation of tides, and we had some data to work with, we included them within this data analysis.
Thanks, Steve. And along the same lines as that question, there's one on how are coastal wetlands stratified within the U.S. inventory? If you could provide more detail on that.
Yeah, the coastal wetlands are stratified into two main classes, estuarine and palustrine, and then substratified into emergent marsh, scrub shrub, and forested. There are other classes which are not vegetated coastal wetlands, such as bare ground and the like, which are not included within the inventory unless we see a vegetated system being converted to a non-vegetated system, in which case we see a loss of stock associated with that. The way we approach the carbon fluxes is that we use country-specific data where applicable for estimating net carbon accumulation rates for tidal marshes, and there's a relatively large data set associated with that. Mangrove ecosystems, for which is also a relatively large carbon accumulation rate data set, some of those mangroves fell under scrub shrub, and so they are recognized as wetlands under the coastal inventory. Some mangroves fall under forestry and are represented elsewhere in the inventory. So for us, a challenge was separating out mangroves as to whether they were falling into the coastal wetland data set or into the forestry data set. In terms of methane emissions, we had to use a tier 1 to tier 2 assumption that the classification for estrine versus palustrine represented a differentiation between methane emissions. Using a tier 1 assumption provided by the IPCC, the coastal wetlands which have a salinity greater than 18 ppt have effectively 0 methane emissions, but those below that salinity have a methane emission associated with that, and that methane emission increases as the salinity decreases. There was a single default value is provided by the IPCC. We were not able at this stage to stratify at a higher resolve level methane emissions across the estuarine interface. And so we made an assumption that estuarine wetlands represented a 0 methane emission, but that palustrine wetlands, we applied a methane emissions associated with that. So there is an error associated with that assumption that could be improved moving forward, but that level of stratification is higher. Sorry, the NOAA CCAP data provides a higher level of stratification than we could have achieved using the NRI data set, which only recognizes one wetland class for estuarine systems. Hopefully that helps with that question.
Thanks, Steve. Next question. Are there plans to include the large areas of inland coastal wetlands around the Great Lakes into the inventory?
Potentially, but not under our analysis. The IPCC guidance is coastal wetlands. It is represented by areas which are subject to tides. And so while in some ways the Great Lakes is also a coastal system, it's not an oceanic coastal system as subject to tides. So for this reason, we have not so far included the ecosystems of the Great Lakes within the inventory. This may be something that might be included as future improvements down the line, but is not included at this time. Good question.
Great. All right. Next one is a comment followed with question. So it's one thing to make analysis and evaluations, and another to be able to include findings into the national inventory. How did you engage the process of mainstreaming these findings in the national inventory? And what are the stakeholders involved in coastal area management? Are they aware of these findings, or how do they react about these findings when you do talk to them?
Maybe this would be an interesting question to pass to some of our NOAA colleagues, and then I might come back.
And then I remind our NOAA colleagues to unmute themselves if they're ready to respond.
You may need to repeat the question, Steph.
Sure. So this is a question about engaging with stakeholders about the results of the inventory analysis and what reaction the coastal management community has about these findings.
Yeah, and I'm happy, this is Ariana. I'm happy to give a shot to that, and then Meredith can follow up. I mean, so far, the inventory was just submitted and finalized and came out in April. So it really hasn't been out very long yet. And we have had 2 webinars on the topic so far that Steve has presented at, this being the second. So this is part of the way we are getting the message out about the fact that coastal wetlands are included for the first time and what are the kinds of findings that we have. So we are working on some of that education and outreach, as we speak. But Meredith, do you want to add to that?
No, I have nothing else to add. This is just early steps, and we would appreciate, in fact, any guidance or suggestions you would have in terms of communicating, reaching out to stakeholders, many of which you may actually be.
Great, thank you both. I'll go to the next question. What is the political significance of the national inventory and the inclusion of wetlands for the U.S.? Do you think it will have any national legal implications?
Yeah, I'll pass that to Noah also.
So this is Ariana. In terms of legal implications, I'm not quite sure what the audience member is referring to there, but in terms of now that the coastal wetlands are included in our national inventory, this is a really significant step forward in that we must now, the U.S. must now continue to include wetlands in our inventory moving forward. And we will always go back to that beginning 1990 level and track forward. So it's a really important step forward in terms of now we have to do a better job of tracking restoration of our coastal wetlands, loss of our coastal wetlands, why are we losing them, where are we losing them, because that's all going to be part of our emissions inventory. There's already been efforts, and NOAA has led a number of these efforts to basically use our additional knowledge about the sequestration and storage that coastal wetlands provide in terms of thinking about how that might be incorporated into the implementation of our existing regulations or policies. So we have definitely worked on that. We've done an analysis of where it's possible to include coastal wetlands in things like the Clean Water Act or the National Environmental Policy Act, et cetera. And we also have done a couple of pilot efforts. Those were both NEPA efforts where we actually have included in a NEPA document, so National Environmental Policy Act, in an environmental impact assessment of what a restoration project out in the San Francisco Bay, what would be the carbon benefits of the different restoration alternatives. And that was part of that discussion and process for that particular restoration project. So we now have a precedent where we have included in a NEPA document carbon benefits of a coastal restoration project. And precedent, as we know, is very important in terms of legal standing. Once you have something as a precedent, you can turn to that and say, look, this has been done. This is not unusual. This is possible. So it is my hope that NOAA's efforts on that front will actually continue to push forward efforts to incorporate carbon benefits of coastal wetlands and other ecosystems, quite frankly, but especially of coastal wetlands, into the way we think about and implement our national environmental policies. But to date, that's still a very sort of nascent process that we're undergoing.
Great, thank you, Ariana. One more question I think we have time for. To meet significant carbon reductions, what type of management or restoration activities could result in, the most bang for the buck if we were to try to prioritize those type of actions?
Good question. Well, it depends upon the scale. Methane emissions, the impounded waters, is a relatively simple restoration activity. If you remove a barrier, avoided methane emissions is probably the lowest hanging fruit. And the reason being, there is no reversal risk associated with halting methane emissions. The methane emissions reductions occur almost immediately once you increase the salinity. And you don't even need vegetation to come back. So you can have, if vegetation does come back, you get additional carbon sequestration, but the methane reductions will occur in the absence of vegetation if the salinity is increased. There are a lot of small-scale impounded wetlands around the U.S. State of Massachusetts, for instance, has, I think, 120 on its hit list, and it has been reconnecting. It's reconnected something like 20 to 40 impounded waters over the last 20 years. At the larger scale, the Mississippi Delta could potentially be one of the largest sources of carbon emissions moving forward, particularly as sea level rise starts to tick up. Now, the plans for the large-scale plans for reconnecting sediment supply to the coastal wetlands of the Mississippi Delta could help avoid emissions for some portion of the delta. And so at a very large scale, that might be one of the more significant activities that can be looked at moving forward. And certainly this is a subject of additional quantification that the US Geological Service is providing. And then at the smaller scale, it is, you know, looking for opportunities where you can restore a coastal wetland and do that on a drained organic soil, because you can have that stop loss effect. So it's looking for the opportunities across the landscape and just trying to enact them.
Great, thank you, Steve. And we had an additional comment on the feed to the effect that the state of Massachusetts has almost 600 mapped tidally restricted wetlands, so perhaps a good place to start. But with that, our time has come to a close. For any questions we did not get to, I encourage you to send an email to one of our speakers. So thank you very much to our speakers today and to all of our attendees for today's webinar. Again, we'll have a recording of this session online, which will be shared to all our registrants. And thank you again, Steve. Thank you, Meredith and Ariana. And have a great afternoon, everyone.